To go so I guess the time has come to start the second talk of the session. So the speaker is Pei from Harvard University, and we see the title on compactifications of 6D relative theories. Please go ahead.
Thank you. Before I start, I would like to thank all the organizers for putting together this wonderful event and for the invitation to speak. It's a great pleasure to be part of this. So I'll be talking about 6D theories and their compactifications. So let me start by telling you a little bit about why one would be interested in 6D theories and what one hopes to achieve by studying their compactifications. So for physicists, this class of theories are very interesting because they have unique physical properties and also because they play a special role in string theory and M theory. On the other hand, for mathematicians, this class of theory are interesting because they are usually very good at uncovering hidden connections between different subjects in mathematics. For example, taking some geometry and topological input, they sometimes can provide for you some hidden algebraic structures, hidden combinatorial structures, or some new geometric objects that looks very different from the geometry and topological data that you started with. In this way, it can serve as a bridge connecting different branches of mathematics. The way that it actually does this is through a process known as compactification. So I will say a couple of words about compactification. So if you have a quantum field theory in higher dimension, let's say 6 dimensions, then you can wrap that on a d-dimensional manifold. So here, MD will be my d-dimensional manifold, possibly with non-trivial topology. And then I can try to reduce the size of this d-dimensional manifold. Then effectively, I will have a quantum field theory in 6 minus d dimensions. The interesting geometric or topological information about the d-dimensional manifold will now be translated into interesting mathematical structures or interesting dynamical structure in the quantum field theory. This way, such theories in higher dimensions can provide a bridge between geometry, topology, and other kind of interesting mathematics. So let me give you a very incomplete and very quick summary of some applications of 6D theory in math. Usually, to have interesting applications, superconformal symmetry will be very convenient to have. There are 2 special classes of theories in 6D that have superconformal symmetry. One class is known as 6D 2,0 theories, and they are classified by ADE Dinkin diagrams. And they have already had numerous applications in math. For example, they can be compactified on 4 manifolds. And the 2-dimensional theory obtained, known as T of M4, turn out to know a lot about the model space of instantons. Studying them can shed some new light on the pioneering work of Nakajima and Waffen-Witten. And this class of theory also provide correspondence between vertex operator algebras and the study of topology of 4 manifolds. So on Monday, Thomas has already mentioned a little bit this correspondence. We can also consider compactifying this theory on 3 manifolds. The theory T of M3 can be used to define new invariants for 3 manifolds or to categorify old invariants. And in the talk by Pavel and Francesca, we have already learned about a new invariant Z hat and the interesting properties they have. And one can also compactify the theory on a 2 manifolds. The topology of 2 manifolds is not as interesting as that of 4 manifolds or 3 manifolds, but nonetheless, you'll get very interesting physical theories, and there will be very interesting mathematics For example, by studying such theory, you will have a better understanding of the hyperkähler geometry of model spaces. And this theory also provides an interesting playground to study curious mathematical phenomena like wall crossing. And there is another connection to VOAs, as was nicely summarized in the talk by Thomas and Tomoyuki. And after further compactification, such theory also had applications in the geometric long length program. And there is another class of theory which actually contain the previous class. And these are 61,0 theories, and they form a much bigger universe. So many such theories are labeled by singular elliptic Calabi-Yau threefolds, which are much richer than just AD-Deakin diagrams. And one may wonder whether they also have interesting mathematical applications. Just like their 2,0 cousins, they can be compactified on 4 manifolds. And it seems that these theories in 2 dimensions, T of M4, obtained in this way, encodes some new invariants of 4 manifolds that are valued in the ring of topological modular forms. One can then consider compactifying this theory on 3 manifolds. And in some examples, one observes that T of M3 obtained in this way seem to give you certain modules over the ring of topological modular forms. And one can also compactify the theory on 2 manifolds. So there has been many interesting physics developments in studying such system. And I have no doubt that very quickly they will have very interesting math applications. So the talk today will not about any of these applications specifically, but it will concern all of this because today I'm going to focus on some universal aspects of compactification of these 60 theories. The tool that we're going to use will be symmetries and their anomalies. And this is based on joint work with 2 amazing collaborators, Sergei Gukhov and Bo Shenxin. So this is still ongoing work, so any comments and suggestions are extremely welcome. So let me first give you a quick reminder for quantum field theory with anomaly. So if a quantum field theory has symmetry, global symmetries, and they have anomaly, the quantum field theory can still be consistent, but it should be more naturally viewed as living on the boundary of a topological theory which lives in 1 dimension higher. For the usual 2 anomaly that we're most familiar with, the topological theory in the bulk is invertible, meaning that its Hilbert space on any d-dimensional manifolds is 1-dimensional. In this case, one will say that the boundary QFT is either absolute or projective. There is a distinction between these, but in this talk, I will not distinguish between actually absolute theory versus projective theory. What I will distinguish is this situation and the situation when the TQFT is non-invertible, meaning that in some cases, the Hilbert space on some D manifolds can have larger dimension. And in this case, we will say that the boundary quantum field theory is relative. For relative quantum field theory, one cannot just define its partition function. Instead, one has to first specify a state in the TQFT Hilbert space. If one had further a set of bases for the TQFT Hilbert space, then one can define a collection of partition functions and assemble them into a partition vector of the boundary theory. So one interesting fact about 60 theories is that most theories that we know in 6 dimensions are actually relative. For example, for the 2,0 superconformal theories, they are classified by AD-Deakin diagrams, and all of them are relative except for the one labeled by E8. And the bulk theory, the topological theory living in 7 dimensions, is described by a 3-form transaminant theory. This is what the action looks like. It pretty much looks like the transaminant action in 3 dimensions, but instead of having a 1-form connection, now the dynamic field is a 3-form U1 gauge field. But the levels are still going to be quantized, and they can be assembled into a coupling matrix. In the case when we are considering 60 2,0 theories, this coupling matrix will be identified with the Cartan matrix of the corresponding the algebra of type ADE. One can further define abelian groups in this way. It is often referred to as a defect group. Physically, elements in the defect groups labels 3-dimensional defects in the 7D TQFT. And these defects is very like Wilson lines in 3D transaminant theory, in that they have braidings and spins. One way to encode the data for braiding algebraically is to consider the symmetric pairing on D. This is sometimes referred to as a Dirac pairing from the boundary perspective. And the spin for these defects can be viewed as a quadratic refinement of this symplectic pairing. So I will denote as Q. Now, given a 6 manifold, by combining the pairing on D with the pairing in cohomology, we can get an antisymmetric pairing in H3 of the 6 manifold. And in the study of quantization of the TQFT on the 6 manifold, it's very convenient to consider the notion of a polarization defined as a choice of a maximal isotropic subgroup. And it is expected that given such a subgroup, denoted as lambda, one can obtain a state in the TQFT Hilbert space, which specify a particular partition function for the coupled system. So our goal today will be to first look at this slightly more carefully and refining it a little bit, and then generalize this to the problem of compactification a manifold with dimension D less than 6. So before doing that, we'll take a slightly different perspective on polarizations. Instead of defining it using group theory, we'll define it using physics as the possible ways to obtain absolute 0-dimensional theory by compactifying on a 6 manifold. And here there's a small caveat. We only consider compactifications that are universal, meaning that this is compactification that can be done for any boundary theory, provided that they are coupled to the same bulk theory. So this is a cartoon of a naive dimensional reduction on 6 manifold. In 60 and 70, the 6D boundary theory has 2-form symmetry. But this 2-form symmetry has anomaly, and that anomaly is captured by the 7-dimensional transaminant theory. After compactification, when we have a 0-dimensional theory on the boundary, you will now have an anomalous -1 form symmetry. And there will be a 1-dimensional TQFT that describes this anomaly. Operators in the TQFT come from wrapping the 3-dimensional defects in the 7D theory on 3 cycles. So here, alpha beta start their life as 3 cycles, And after compactification, they become operators acting on the Hilbert space associated with the 6 manifold. And in general, they won't commute. The phase that describes their failure to commute is proportional to the pairing between alpha and beta. So one way to get absolute theory in this setup is to gauge part of the -1 form symmetry on the boundary. Since this symmetry is anomalous, one cannot gauge all of it. One have to gauge a subgroup. And to be consistent, this subgroup has to be anomaly-free. And that's the same as being isotropic. And further, if you want to get an absolute theory, the bulk TQFT has to become invertible after gauging. And that's the same as the maximal condition on the subgroup. So from the bulk perspective, gauging such a subgroup on the boundary is the same as acting by the projection operator defined in this way on the boundary. And it will be well defined because lambda is anomaly-free, and it will project onto one-dimensional subspaces because lambda is also maximal. Further, one can define a collection of projection operators with background field B. B will be valued in the dual of lambda. And one can check that they are indeed projections onto different one-dimensional subspaces with no overlap. Therefore, this collection of projection operators give you a decomposition of the Hilbert space. But that's not the same as choosing a basis yet, because choosing a basis would require choosing phases in each one-dimensional spaces. And in general, there can be some phase ambiguities, and there can be obstructions of choosing canonically the phases. One can only choose canonically the phases if the dual group lambda check is also anomaly-free. And that's the same as saying that this short exact sequence split, which is the same as saying that H3 can be decomposed into lambda plus a lambda bar. Lambda bar will be isomorphic to lambda check, and it can be viewed as the lift of lambda check into H3. And the basis will actually depend on this particular lift. And then we'll have well-defined basis in the Hilbert space, which can now be identified with the C-span of lambda bar. We will use this notation for the basis vectors that are labeled by B. And each of them give you a component in the partition vector. So for another polarization, the partition function will be a linear combination of these bases of the these building blocks. And one can get a formula like this by acting the projection operator on a particular basis vector. But actually, there is an ambiguity in defining this projection operator. And that's the same kind of ambiguity in ordering operators that puzzles founding fathers of quantum mechanics about 100 years ago. So if you upgrade alpha to an operator alpha hat and beta to beta hat, so what happens to alpha plus beta? Well, you can send that to alpha hat times beta hat, but that's different from beta hat times alpha hat. What you really want to do is to send it to alpha hat times beta hat times square root of the phase that appear in this commutation relation. So to do this consistently, we need to choose a quadratic refinement. This will be given by a quadratic function Q on lambda prime, and it will have some compatibility property with the pairing. And the partition function will actually depend on Q, because now the projection operator will depend on Q. And it will be simply a linear combination of the building blocks like this. So to give a quick example, consider the 6 manifolds being S3 times S3, and D being Z2. Then H3 will be a product of 2 Z2s. We will refer to the first Z2 as electric and the second Z2 as magnetic. The Hilbert space will be 2-dimensional, and it will be spanned by the 2 vectors if we have chosen electric basis. And there are going to be 3 maximal isotropic subgroups. You can take the first Z2, second Z2, with diagonal Z2. They are all maximal isotropic. And anticipating connection with 4-dimensional physics, we will refer to these 3 choices as SU2, SO3 plus, and SO3 minus. But each of them has 2 projective refinements. So in total, there are going to be 6 polarizations. And they correspond to these 6 different vectors in the Hilbert space. And they can be maybe referred to as the SU2 theory for the 0, spin SU2 theory for 1, and SO3 theory with a Z4 valued discrete theta angle for the remaining 4. Since we have 6 different vectors in a 2-dimensional Hilbert space, any 3 of them will have a linear relation. So you will have relation between partition functions like SU2 equals to SO3 plus, well, SO3 0 plus SO3 2. And you'll have many other relations. These are relations that is very similar to what you have seen in Eric Sharp's talk on Monday. And these relations are universal in the sense that it comes from the bulk TQFT and will be valid for any boundary theory that can couple to the bulk TQFT. Another interesting feature of this is that there will be an SL2Z action acting on H3. So it will act on these maximal isotropic subgroups, and it will act on these 6 different states and the 6 different polarizations. And you can easily work that out, and you end up this diagram. And after lifting this to 4 dimensions, this will agree with a conjecture in the literature found when they study different versions of SU2 theory on non-spin manifolds. And this relation is also universal. The action of the mapping class group will be exactly the same if the bulk theory are the same. For example, E7 would couple to the same bulk theory, and you have the following action of mapping class group for the E7 theory. To give another example, consider again 6 manifold being product of 2 3 spheres, and D being now product of 2 Z2s, and the pairing is between the 2 Z2s. This would be relevant if you want to study the compactification of the 62,0 theory labeled by spin 8. Now there will be 15 maximal isotropic subgroups, and each of them will have 4 quadratic refinements. So in total, you will have 60 different polarizations. The Hilbert space will be 4-dimensional in this case, spanned by these 4 vectors, and they correspond to different versions of spin 8 theories. And similarly, there will be 4 different versions of SO8 minus theories given by these 4 different vectors. And again, one can study mapping class group action. There will be 7 orbits for maximum isotropic subgroups, and there will be 16 orbits for polarization after the quadratic refinement. So one example.
Sorry to interrupt you too. Edward Witten has his hand up. Ed,
Yeah.
if it's not too late, would you unmute yourself and ask the question? Yes, can you unmute yourself, please? So I have just noticed that, but his hand is probably was not.
Only now I could unmute myself. Until a second ago, I just wanted to, first of all, I hadn't intended to interrupt your lecture. I'm sorry. I thought I'd ask at the end.
No problem.
But I wanted to understand intrinsically what you're constructing. And I thought what you're constructing might be absolute theories in 3 dimensions that can come by compactifying this relative theory in a single S3. Because we called it S3 times S3, it could have been anything times S3 and would have led to a similar discussion.
So,
in 6 dimensions, I don't quite know what you're discussing, but I thought maybe you're discussing relative theories, sorry, absolute theories in 3 dimensions.
So here we are constructing absolute theory in 0 dimensions. Later we'll do the same, but constructing absolute theory in higher dimensions. In this talk, I actually won't be talking about 3 dimensions, but I will talk about 5 dimension, 4 dimension, and they will share a lot of similarity with this case in 0 dimensions.
Oh, you said, I see.
So polarization on S3 times S3 will provide for you absolute theory in 0 dimension. And in some cases, it might actually come from an absolute theory in higher dimension. But in this case, I'm not absolutely sure whether they can come from absolute theory in 3 dimension. Shall I continue? We can have a longer discussion about it later.
Sorry for this interrupt, but I think it was useful. And then you can continue discussion after your talk. Maybe, yeah. Could you please continue? Sorry.
Yeah. Okay. So one particular orbit without refinement is given by the following, and this agree with how the corresponding 4D theory transform. But these 4D theories are theories defined on spin manifolds. And over this orbit, there will be a 4-fold covering by 2 orbits that looks like this. This is what one gets after the refinement. And each choice of maximal isotropic subgroups is now covered by 4 different polarizations, which differ in their quadratic refinements. And again, this action of mapping class group is universal. So you will find exactly the same action in the case of spin 8n. So one thing that is special about spin 8 is that it has triality. For spin 8n, naively it should not have triality, but all the orbit is compatible with triality because they simply couple to the same bulk theory. So now we will study compactifications on D-dimensional manifolds with D less or equal than, let's say, less than 6. And we want to generalize slightly the notion of polarization to a notion of polarization on a D manifold. Before, we have defined the set of polarization as ways of compactifying to get absolute 0-dimensional theories. Now we simply generalize that to ways of defining of compactifying theory to get absolute 6 minus D-dimensional theories on a D manifold. And again, we only consider reductions that are universal. These are reductions that make sense for any boundary theory coupled to the same bulk theory. Notice that compactification of absolute theories is unique. So one will have a map from polarizations on D manifolds to polarization on D manifolds times another manifold. So using this, you can view a polarization on D manifold as a family of polarizations on manifolds of the type MD times M6 minus D. So there will be a family of usual polarizations. And this family is supposed to be functorial in the M6 minus D direction. I will comment on what that exactly means later. So a difference between higher dimensions and zero dimensions is that now you will have two different types of polarizations. The first type is what I will refer to as pure polarizations. And they are obtained by choosing a subgroup of the cohomology group of MD with D coefficient. And they are required to be trivial under the pairing. And it can be decomposed into different graded pieces. And using this, the maximal isotropic subgroup, lambda M6 minus D, will be given by the image of this map in cohomology. But actually, there will be other possibilities, and there will be mixed polarizations. So to see this more concretely, let's look at the example. Let's consider polarizations on a circle. And we will take D to be ZP, with P being a prime, to slightly simplify the problem. So given a 5 manifolds, any polarization on S1 would specify for you a maximal isotropic subgroup inside this cohomology, which can be identified with H2 plus H3 of the 5 manifold. And it turns out that there will be two pure polarizations. One corresponds to the choice that L equals to H0 of the circle. For this choice, this isotropic subgroup will be H3 of M5. And it can be perhaps referred to as the SUP theory, because this is literally what you get if you reduce the 2,0 theory of type AP minus 1. There's another choice of pure polarization given by H1 of the circle. This corresponds to this choice of the of a maximal isotropic subgroup inside H3 of the product. And this is perhaps can be referred to as the PSUP theory. But actually, there are going to be mixed ones, and they are constructed using the following. So you take any elements inside H2 and look at its image under the Boltzmann homomorphism to H3. And you multiply that by K. So this defines for you an element in this sum, and you consider all such elements. This also turns out to form a maximal isotropic subgroup. And for K that is not equal to 0, it's not given by any L. So this will be an example of a mixed polarization. And these theories physically can be related to PSUP theories, but with a discrete theta angle. So before pursuing more examples, we will make some general comments about symmetry and spectrum. So for pure polarizations, the degree D minus n piece of L will label charges of operators of dimension 2 minus n. So in the 2D example, for L being H0, L can be viewed as possible charges of the Wilson line in the SUP theory. For the other choice, L will be H1, and these label charges of the magnetic string in PSUP theory. But how about mixed polarizations? What symmetry do they have? And what's the spectrum of operators? The spectrum for mixed polarization, or in fact, for any polarization, can be studied by defining a spectrum group. So it's a subgroup of the cohomology of MD. And it's defined as a union of the image of lambda M6 minus D and the following map in cohomology. So I won't say more about the construction, but I will remark that you will get back L for the pure polarizations. So it's a good measure for the spectrum of operators, at least in the case of pure polarizations. But if you're considering mixed polarizations, you will actually get a spectrum group that looks like it's improperly quantized. In other words, this pairing will be non-trivial as P. And physically, this would indicate that this theory seems to contain operators that does not satisfy Dirac quantization condition. So how can this theory be consistent? It turns out that the theories are consistent because some of the theories does not exist independently. They only exist on boundary of some other theories. And this can be interpreted as the Witten effect or generalization of the Witten effect in the presence of discrete theta angle. In the 5D theory example, on the boundary of the magnetic string, you will have something that has fractional charge under the one-form symmetry. So it can be a fractional Wilson line, for example. And the fractional Wilson line will not be properly quantized, but that's completely fine. So to get the correct symmetry for the theory, we need to consider a subgroup of independent objects, and the symmetry will be the dual of this. So for example, in the PSUN theory, with discrete theta angle, you will have two-form magnetic symmetry, but not one-form electric symmetry. So we have defined the notion of polarization, but how to actually classify them? For pure polarizations, one can proceed by looking for all such subgroups that is trivial under the pairing, similar to what you would do when you study polarization on a 6-manifold. But how about these mixed polarizations? It turns out that they can be classified by relating them to SPD phases, which are the same as invertible TQFTs with symmetries, but in 6 minus D dimensions. So how can this be done? The way to see this is to consider this relation between partition functions. Now I've added in the dependence on the 6 minus D dimensional manifold. So now the phase is not just a function of alpha. Now it's also a function of the 6 minus D dimensional manifold. But you want functoriality, because actually this will be certain amplitude in the 7D TQFT. So that would imply that this phase itself is a partition function of an invertible TQFT with symmetry. And this can be classified and by relating them to cobordism groups. If the theory corresponding to a polarization lambda is given by a Lagrange description, let's say a gauge theory, then very often this invertible TQFT has an interpretation of a discrete theta angle. So now let's look at compactifications on 2 manifolds. Example 1, you can consider 2 torus And first, you look at pure polarizations. They are given by choices of two subgroups of the cohomology of T2. One is an isotropic subgroup inside H1 of T2. Another is a subgroup inside H0 plus H2. We actually have already encountered this group because this is exactly H3 of S3 times S3. And that's why I was using 4D notation 10 minutes ago when I was discussing zero-dimensional physics. It will be literally just the same in 4 dimensions. So all this SL2D transformation apply to the 4-dimensional theory. For the second part, it will be the same actually as the cohomology of S1. So that's also something familiar and something that we have seen before. So for 62,0 theories, if you compactify on T2, you'll get a 4D gauge theory with a matter. To keep track of all the symmetries, it's a good idea to make sure that one of the scalar is actually compact. Then the choice of the first subgroup L1 will tell you what is the global form of the gauge group and what is the discrete theta angle. And the second choice of L0 will tell you what is the global form of this compact scalar. It can be a group that is different from G. And depending on the form of G0, the theory can have 0-form symmetry and 2-form symmetry given by the center of G0 and pi1 of G0. And they can also sometimes have mixed anomaly. An example of a theory that one can get by compactifying is a SO3 minor theory with a SU2 value scalar, for example. And these are the pure polarizations, but there are many mixed polarizations. And there will be charged objects in dimension 0, 1, and 2. And on the boundary of the 2-dimensional objects, which I call axion strings, there will be fractional Wilson and 2 lines. And on the boundary of Wilson and 2 lines, you will carry fractional charge under this symmetry. This is general feature for theory obtained from these mixed polarizations. One can also consider a genus G Riemann surface. And the problem will be almost identical, except that L1 is now an isotropic subgroup inside H1. This problem was considered in a paper by Tachikawa a few years ago with the choice that L0 is the degree 0 piece. But there are, again, going to be many mixed polarizations. And they differ from the standard one by some choices of discrete theta angles. And this would give you some new class S theories. So if you are amazed by the interesting connection between class S theory and mathematics, you should try generalizing all of this to these new class S theories. So I think I'm running out of time. So I only have a few quick comments, but maybe let me just show all of this. So 2 comments is about compactification in 3 and 4 dimensions. The third comment is about isometry of MD. I didn't discuss this, only discuss mapping class group action, but they're also interesting and they act in a very non-trivial way. Sometimes they act in a way that it combines with other symmetry to form a higher group symmetry. Even for compactification on S1, you can have actually an anomalous 3-group symmetry. Oh, there are many more comments, but since I'm over time, so thank you.
Thank you, Du, for this nice talk. I'll now unmute everybody. So are there any questions? Yes, I see Nicola Didushenko has a question. Yes, please go ahead.
I do.
Nicola.
Nice talk.
Thanks.
So I actually have a few questions. The first one, I feel like you actually intentionally designed it to provoke a question. So I'm asking this: what is the -1 form symmetry?
Oh yeah. So -1 form symmetry is not like any other symmetries. So
Excuse me, not to interrupt you, but I have to mute you all, and then you two guys have to unmute yourself. Sorry for that. So Mikola, I see you are unmuted. Yeah, and so
okay, I think I'm also
go
now
ahead.
muted.
Sorry
Yeah.
for the switches.
So -1 form symmetries has symmetry defects being space filling. So they are transformation on the theory. So if you have discrete theta angle, acting by a -1 form symmetry can change that discrete theta angle.
Mm-hmm.
So in this particular zero-dimensional example, there will be indeed some discrete theta angles. And then you can shift this discrete theta angle by acting by -1 form symmetry.
I see. So there are no charged objects. It's just an operation on the theory.
Yeah, exactly. Exactly. So that's why I put this in quote.
Mm-hmm. Another question, but I think you already kind of answered, because you, at the beginning, you were talking about mapping class group, and I was wondering what is of what, but then it's probably T2, right? It doesn't have any interpretation in terms of S3 times S3.
Well, for the case of S3 times S3, the mapping class group of S3 times S3 still acts. And actually, the mapping class group of S3 times S3 can be quite complicated because of exotic phenomena. But the action on homology will factor through the quotients to SL to Z. So it will actually be the action of mapping class group of S3 times S3. But that already
is it clear?
captured.
Is it clear what's T? Like S is probably exchanges the two S3s.
Well, it will be the same. You can still do exactly the same as the two-dimensional torus. So the pi 3 of S3 is still Z, just like pi 1 of S1.
Okay. And final question. So just to understand, so what part of this is known, what part of this is new? Do I understand that correctly, that the main result is about computing polarizations and products of manifolds and identifying the physics interpretation?
Yeah, exactly.
Okay.
All right, thanks.
Well, thank you, Mikola. And the next question is by Kumrun Bafa. Kumrun?
Hi, Kumrun.
Hi, nice talk. I have a question. The 61,0 theories, there are also the little strings that are interesting. And in those cases, you get matrix Kij that you had, which are have null directions. Does that introduce an interesting story for you for polarizations in that context?
So in that case, there will be a degenerate direction in K, is that correct?
Yes.
Then the theory will not be completely topological. You will have some probability degree of freedom. So one probably need to take into account of that. Provided that somehow one can remove this, then the same story can still apply. But with this massive degree of freedom, then one need to maybe find a different way of treating them.
And also, when you say topological, so you were studying in the first part, you were specifically keeping some supersymmetry, but in the more general setup you were describing, supersymmetry did not play any role. So you were talking about the more general topological aspects, if I understood correctly.
Yeah, exactly.
Are there any specific aspects of preserving supersymmetry that enhances the structure you're talking about, or just orthogonal to the questions we were talking about?
Sometimes there can be enhancement. So for specific theory, usually there are more things that one can do in the compactification, and symmetry can also be enhanced. But so far we have been focusing mostly on these universal aspects. As long as the boundary theory can be coupled to the same bulk theory, it does not matter too much whether it's supersymmetric or non-supersymmetric, or having 1-0 versus 2-0 supersymmetry.
Okay, thank you.
Okay.
Thanks.
Well, thank you, Kumrun. The next person is Arnav. Can you please unmute yourself? Yes, go ahead.
Yeah, hi, can you hear me? Tell me if there's an issue with my mic.
I can hear you.
Okay, cool. Could you just give me an example of what the Hitchin system looks like for one of your more exotic class S theories, like the Coulomb branch of the moduli space in R3 process 1 for one of your mixed polarizations? What happens to the Jacobian with the spectral curve type description?
Yeah, okay. So there are, one can ask this question at different level. So first of all, there are pure polarizations on sigma times T2 that are still kind of exotic. So there are some standard ones giving rise to SU, for example, SU2 Hitchin moduli space. And there's another one giving you to SO3 moduli space. And then SU2 moduli space will have different quotients. And many of these pure polarization will be a different quotient of this. And to keep track actually of all the symmetry, it's a good idea maybe to consider a multiplicative version of Hitchin system. And then one can often relate all these pure polarizations by gauging. And from the target point of view, this is basically doing quotient or covering. So, but there's also mixed polarizations. I don't completely understand the geometry of the moduli space in that case. So I think it would be a very interesting question to ask. So the mixed polarizations, of course, at level partition function, you'll be linear combination of those of pure polarizations. But the geometric objects or algebraic objects associated to them can be quite different.
Oh, is it still going to be like essentially the same geometry, but just quotiented in a slightly different way? Or do you think it really might be twisted up, genuinely some different vibration stuff?
I think they should not be simply be just quotients. There can be more structures.
Oh, thank you.
Thank you, Arnav. The next speaker is Pavel Putrov. Pavel?
Pavel?
Yeah, go ahead.
I have a bit of technical question. So you say that you need to kind of to define a physical system, you need to fix a quadratic refinement of
yeah, exactly.
On a D. But do you consider certain equivalence, some equivalence relations on a quadratic refinements?
So I have already defined it in a way that they are all equivalent. So they are labeled by like two torsion elements in the dual of lambda prime. And you can see that each of them are actually inequivalent. But there's a way to do this in 7D physics by introducing some background field. In that language, there will be a lot of redundancy. But what I described will be like the thin quotient by all the redundancy. Okay. So by definition, for two different quadratic functions, they will give you different states in the Hilbert space. So we give you different partition functions.
But for example, like if I want to compare with kind of Spincher-Simon theory in 3D, I think you also have to specify, you have to pick a quadratic refinement of this co-kernel of the level matrix, but you also, this quadratic refinement should satisfy under Gauss law constraint. And
right.
Gauss some constraint.
Yeah, exactly. So so what I described here are actually theories that are not like spin transamination theories. So in that case, you need to find some Z2 extension of D. And then indeed, there will be a more interesting story. So I think for 2,0 theory, this is good enough. For 1,0 theory, indeed, one might in general consider along the line that you suggested.
Okay, thanks.
Okay, thank you, Pavel. Now, Ed Witten, please.
Could you explain again the distinction between pure and mixed polarizations? Say when you're compactifying on a 2 torus? It's not the case that one gives a relative theory and one gives an absolute theory in the lower dimension, I assume.
They all give absolute theories.
Okay.
So I think it's perhaps simplest to do this in 5D. It's of course also possible in 4D. Many 4D ones are actually just dimensional reduction of these 5D absolute theories. Right. So here, the two pure ones is given by SUP theory and PSUP theory.
Yes.
Okay, so, but you can introduce discrete theta angle term
Yes.
in the PSUP theory. If you have a W2 for the gauge bundle, you consider W2 times boson of W2 with a coefficient. That's an absolute theory, and this discrete theta angle have Witten effects to introduce some fractional charges on the boundary of other objects.
So, okay. What's the principled reason to call one pure and one mixed?
So pure ones come from a subgroup of the cohomology of SD.
I see.
And geometrically, they correspond to, so choosing a T-type state corresponds to choosing some 7 manifolds. And they're particular nice type of 7 manifolds, such that you just need to choose.
You choose a 3 manifold whose boundary is the torus. Or
yeah, exactly.
Or something.
Yeah, in this case, a disk with a boundary being S1. But
well,
yeah, but the mixed ones are going to be more complicated 7 manifolds.
Okay, but okay, what you've listed on this page are all the are presumably meant to be all the Lagrangian subspaces of the middle dimensional cohomology of M5 times a circle that you can describe universally.
Yeah, yeah, I believe these are.
What's a precise form? Is there a precise formulation of that statement? Or are these just, I mean, I can see that these are the ones we can think of, although the mixed ones are harder to think of.
So the mixed ones can still be classified using SPD phases. And in this dimension, the only SPD phases that we can think of are just of this type, given by W2 prime delta W2 prime. That is relevant. So I believe that in this dimension, using the connection with cobordism group, one can completely classify these SPD phases. Then one can argue that these are the only mixed ones.
SPT phases of what, by the way? Okay, I think I'm asking too many questions though, and we're running out of time. So maybe I should talk to you privately.
Right, maybe you can continue that privately or in a breakout.
So to say just very quickly, so these SPD phases are these coefficients that appear in this decomposition. And they have some interpretation as some amplitude in the 7D TQFT. And because of that, they are actually behaving like TQFT in 6 minus D dimensions. And if this can be written down concretely as a function of B alpha, then it will just look like a discrete theta angle term in the theory that deform the theory.
Okay, thanks.
Yeah, okay.
Thank you.
Due to the fact that we are approaching the full hour, there is one more question by Ali Sheffer. If it can be short and sweet, please, Ali.
All right, so I'll be very quick. What does it physically mean to make a choice of a quadratic refinement? And sometimes you were making that choice, sometimes you weren't.
So in general, we always want to make the choice. So in 0 dimension, we always want to make the choice. The problem in high dimension is that you want a choice that is compatible with functoriality. So you actually, so here the phases actually take into account of the quadratic refinements.
And what does it physically mean to make a choice like this?
Yeah, so in this reduction, there are background fields. And you should take the point of view that all background fields are more or less equal. So you need to consider all of them. So these are background fields that Z2 valued and coupled to C in the term like C dx. And they have the property that they will not change braiding, but it will change the spin of defects. So you need to ideally consider all of this. But you, on a general manifold, you want to consider those that are behaving nicely in the TQFT fashion. So, but you actually see some of this here. So let's remember that the SO3 plus theory and SO3 minus theory are distinguished by a discrete angle that's written down using Pontryagin square.
Yeah.
And that's exactly quadratic refinement. So quadratic refinement in lower dimension is like square divided by 2. But in higher dimension, it's a cohomological operation like Pendragon square.
All right. Thank you.
Okay, thank you. Let me unmute you all, and let's thank Du again for this excellent talk.
Thank you very much.